good morning. In my last lecture, I was talking about BET isotherm, a multilayer adsorption isotherm. So, let us continue the same today for the derivation or understanding the isotherm. So, as I said earlier also that Langmuir adsorption isotherm, which is for the not for the multilayer adsorption, rather a monolayer coverage, and BET is the extension of Langmuir taking care of that multilayer adsorption, right. So, both monolayer and multilayer adsorption is possible in BET isotherm, and the adsorbed layers, when you look at the in the Langmuir isotherm also we assume that the surface is uniform. In BET also the same assumption has been taken, the surface is uniform, adsorption takes place. So, heat of adsorption for the first layer is same, but when you look at the multi-layer it is nothing but the condensation of the molecule. So, therefore, the heat of adsorption for the subsequent layer will be different than the heat of adsorption in the first layer, because first layer is on a gas molecule adsorbs on the surface of the solid, but in the second case the condensation is on the layer of the liquid which is already there on the surface, right. So, that is basically heat of condensation of that gas molecule. So, this is the difference. So, heat of adsorption here and heat of adsorption for each subsequent layer is taken as the heat of condensation. So, suppose there is a big difference between delta H adsorption and delta H desorption, this heat of condensation, then it resembles to your Langmuir adsorption isotherm. So, that term we will talk later, because here this C which is defined is a term related to heat of adsorption on the first layer and condensation in the subsequent layer. So, this is what the exponentially related term for the multi-layer adsorption, where the heat of adsorption and heat of condensation in subsequent layer is different. So, overall derivation of BET isotherm we have talked last time, and let us see the steps which take place during the BET isotherm. So, we just talked that a model where we are assuming that each layer is formed. So, this is the bare surface. So, we are saying the fraction of the bare surface theta is 0, theta 1 is the fraction of the surface where the monolayer is formed, theta 2 is the fraction of the surface where two layers are formed, and so on, right. So, this surface, total surface of a solid is divided into areas that are uncovered, theta 0 covered by a monolayer, covered by two layer, and that summation will be nothing but if I just add all these monolayers here, that is my surface area or your BET surface area or surface area of the solid surface. So, we are interested in determining this total number of molecules which adsorbs on the surface and the surface which is bare, and then we can just add that, right. So, that we have just discussed last time in terms of the fraction of the surface which is covered per unit area, right. And isotherm when we are talking, so we are talking a dynamic equilibrium between the layers, right. So, when you have a bare surface, the first surface which is your bare surface here, so molecules are evaporating from there and adsorbing here, right. So, at equilibrium, when I say that rate of adsorption on the first layer or rate of adsorption on the second layer, so when there is an equilibrium, adsorption equilibrium, the net rate of adsorption is 0. So, rate of adsorption will be equal to rate of desorption at that, right. So, when we are talking the BET isotherm, because it is a multi-layer, so there will be a dynamic equilibrium among these layers, right. So, for bare surface when I am talking, so whatever the molecule which adsorbs here, desorbs from here, they will come and adsorb here, right. So, it means rate of adsorption on the bare surface which is proportional to the partial pressure, right, which is proportional to the fraction of the sites vacant, right, that will be nothing but the whatever the layers which are desorbing from this, right, evaporation. So, evaporation meaning the desorption, and adsorption when I am saying, or I will say the condensation, right, condensation of the molecule. Same thing when I talk this layer which is the second layer. So, whatever the molecule evaporates from here, they will come here and adsorb, and whatever the molecules which evaporates from here, they will go there, right. But when I say in general and equilibrium, so whatever the rate of evaporation from there will be equal to the rate of adsorption on the lower layer, right. So, that is what the meaning of dynamic equilibrium, and we have already made certain assumption that in this the delta H is different, but when the adsorption or desorption takes place from these layers, the heat of adsorption is equal to heat of condensation or liquefaction, right. So, this is for the bare surface which we were discussing last time also. So, rate of evaporation from first layer, right, which is first layer I am saying evaporation. So, this is desorption rate. So, rate of desorption from first layer is nothing but the fraction of the sites which are covered in one first layer, right. So, that is k minus 1 times theta 1, right, and that will be equal to rate of condensation on a bare surface. So, rate of condensation means adsorption on that bare surface, which will be proportional to the fraction of the sites which are available on the surface. So, bare sites, right, vacant sites, and pressure of the gas, partial pressure of the gas times the whatever the rate constant, right, adsorption rate constant. So, this is for the bare surface or equilibrium on a bare surface, and when you look at for the subsequent layer. So, this is for the first layer here. So, for first layer now we are talking the layer 2, right, from where the evaporation will take place and it will adsorb on the first layer, and from first layer also evaporation will take place, which will go to 0 layer, right. So, that is what I said last time also, that there for ith layer we have to go with I minus 1 and I plus 1. From I plus 1 will be the evaporation, and from on ith layer there will be evaporation, and it will go to the I minus 1 layer condensation, right. So, this is what the meaning of dynamic adsorption equilibrium. So, rate the same equation what I said here, that rate of condensation on the bare surface plus rate of evaporation from the second layer, right, will be equal to rate of condensation on the first layer plus rate of evaporation from the first layer. So, for a first layer I am talking second layer. So, second layer will have some evaporation. So, evaporation from the second layer, right, and when I talk a first layer, from first layer also there is evaporation which is here, right, and whatever the molecule which evaporates from the first layer, they will go to a lower layer. So, they will come on the bare surface, right, and this is the term which is from second, it will come to the first, right. So, again adsorption equation means nothing but k 0 times p times theta 0, fraction of the site which is vacant. For the second layer again this will be that rate of evaporation when I am saying. So, will depend on the fraction of the sites which are covered. So, k minus 2 times theta 2, because it is the evaporation desorption. Here again condensation on the first layer. So, adsorption rate constant, first layer rate constant times pressure times the theta 1, right, which is related to your, because on that layer the fraction is being adsorbed, it is a multi layer, right. So, adsorption is possible, that is what it is not Langmuir adsorption isotherm, right. So, even the sites are available theta 1 which are nothing but the adsorbed molecule, but here the delta H or heat of adsorption is equal to heat of liquefaction, right. And the last term which is here again rate of desorption from the first layer, which is desorption rate constant times the fraction of the sites which are already covered. So, if you just look at this and this, so k minus 1 theta 1 is equal to k 0 p theta 0. So, your equilibrium relationship, because these terms are equal. So, you have just k minus 2 theta 2 will be equal to k 1 p theta 1, right. For so, we can generalize this equation now, because this equation k minus 2 upon k 1 is equal to your simply p times theta 1 over theta 2, right. So, or in general I can write for any ith layer you will have k minus I theta I is equal to k I minus 1 p times theta I minus 1, and we assume that because the same surface when we are talking about 0 layer, the surface is similar. So, k 2, k 3, k 4 which are the rate constant for adsorption, they are similar, right, same. The same thing has been shown in the different model that what we have discussed is the reality is something like this, right. But we have assumed that they are disciplined layers, one layer, two layer, second layer, but in reality there may be some surface which is vacant, but in total we are calculating the fraction of the surface which is vacant and fraction of the surface which are covered by different layers, right. So, sigma of theta I, because it is a summation of the each mono layer. So, that will be 1, right, total surface, right, and number of molecule adsorbed if you want to calculate for a given concentration of given pressure that at saturation, and Nm is the when the monolayer forms, right. So, in multilayer this can be more than Nm, right. In BET this when the monolayer forms this will become saturated, Langmuir it will become saturated, right. So, in BET it can be here when I add this I theta I when I just wrote yesterday, that can be cannot be 1 summation, right. Sigma of theta is 1, but I theta is because 1 layer plus 2 layer 3 layer. So, that can be more than 1, right. Same thing here. So, number of molecules which are adsorbed is nothing but monolayer coverage times the layers which are the formed, right. So, theta 0 is the vacant, this is the two layers formed here, there are 3 layers. So, this is nothing but I times sigma of theta I, right. So, for first layer we have already seen now. So, we have written the equation K adsorption, right, times theta 0 times P. So, this is the rate of adsorption on bare surface and this is the desorption from the first layer, right. So, the same equation which we have seen before. So, we have developed a relationship like this and then we have just this equation for any nth layer. So, we have already assumed that adsorption equilibrium constants K 1 for the first bare surface, that is K 1 0 e to the power minus delta H adsorption upon R T. For subsequent it is delta H 1 upon R T, which is something equal to the heat of condensation, right. So, the derivation if you look at that isotherm which we are talking, something like BET isotherm, you know now P upon V into P 0 minus P is equal to 1 upon V m C plus C minus 1 over V m C times P by P 0, right. This isotherm which we have just seen here, this one, right, similar to this one, that is the same expression and written in a linearized form. So, that is what we want to check or develop the expression something like this. So, quickly I will show you some salient points here. So, what we are assuming here that there are total number of sites which are n 0 on the surface, right, which because you are relating the number of gas molecule adsorbed on the surface, right, with the whatever the surface which is covered, because we are saying the number of molecules, if it is known to us, then we can multiply it with the area of one molecule, right. So, that is what we have seen last time, that surface area will be S g if I write BET surface area. So, we represent it sometime like this based on the isotherm is equal to simply if I know some volumes of the gas which has been adsorbed when monolayer has formed, right, and if I know some reference temperature or STP when this volume is known, right, 1 gram molecule of the gas which is adsorbed at say STP, right. So, this is 22,400 centimeter cube per gram mole of the gas, right, per gram mole of the gas. So, this is basically that at this condition, whatever the condition, right, V m is the number of molecules of the gas adsorbed, and you know that at standard condition this is the volume of the gas and this volume contains the Avogadro number, right. So, how many molecules are available in this volume, that is calculated, and if I just multiply with the area of one molecule which we have seen yesterday, alpha the area of one molecule, say as I said for liquid nitrogen molecules it has the area 16.2 angstrom square, right. So, that is your surface area, total BET surface area, and this is what we are looking from this isotherm, right. So, the same thing here, that our interest is that either you get this V m monolayer coverage or find out the N 0 into V m, that is at this, which is number of molecules which are adsorbed on the surface basically, right, when the monolayer forms. So, this is our interest. So, and if you look at here, this is the total number of molecules of the gas when multi-layers formed, right, because the as I said that the formation is nothing but a single monolayer, but ultimately we are calculating this V m. But when I write Na or Va, that is not a monolayer coverage, that may be more than that, because in Langmuir it is monolayer, but in BET isotherm this has gone like this, right. So, your monolayer has formed here. So, we are interested in finding out this V m or whatever N m number of molecules at this condition, not this N t, right. but since number of molecules are adsorbing as a multi-layer. So, we have to calculate those total number of molecules and then correlate it with the Vm. So, keeping that thing in mind, so total number of molecules which comes on the surface, right, or fraction if I calculate, or N0 is the number of molecules multiplied by each number of layers, right. So, you can calculate the number of molecules or sites. I am talking, I am collating it with the number of sites on the surface, right. So, the number of atoms adsorbed is given by this. So, which can be used to calculate the surface area. So, and this is known to you that if you add all the monolayer, the summation will be 1, theta 0 plus theta 1 plus theta 2, that is going to be 1, because there we are talking only monolayer, but when we are talking theta 0 plus theta 1 plus 2 times theta 2 plus 3 times theta 3 and so on I theta I, which I said, right, that is not going to be 1, right. So, we have just assumed the dynamic equilibrium, and then I have just used this basic kinetic theory of the gas, which is generally used because it is related to the sticking probability, right. So, the same thing when I write this F, it is something which is related to the flux, how many molecules of the gas which come to the surface and adsorb, right. So, number of molecules which strikes onto the surface and adsorb, which can be true for chemisorption also when you talk a chemical reaction or a chemical reactive gas like hydrogen and comes onto the surface of the solid. So, this is simply representing the incoming flux per site, right, and related to your sticking probability, right. So, and this is defined by P upon N0 times the square root of 2 pi m k b t, right, where m is the molecular weight mass of the atom, you can say, right. So, per unit atom or molecule, k b is the Boltzmann constant, right, T is the temperature in degree Kelvin, P is the pressure of the gas, right, and N0 is the Avogadro number, right. So, this is the probability of the gas which is related to basically a pressure of the gas, right. So, that is why instead of writing this, when you write the rate of adsorption, you write the expression k 1 times P, right. So, that k 1 is related to this, right, the term which is other than pressure, right. So, constant for the adsorption which you write, and that is related to something like collision theory, right. You calculate that pre-exponential factor and then you correlate it. So, and EID we are talking adsorption because this temperature related parameter will come from the activation energy of the desorption reactions, right. What is the effect of temperature? So, that is the desorption. So, EID I am assuming that it is the energy for desorption. So, the same equation what we have written earlier, because now I am talking a dynamic equilibrium. So, at equilibrium for any layer d theta I by dt will be 0, right, because when there is equilibrium. So, within that multi-layer there some molecules are evaporating, some are adsorbing, right, but there is no net gain or loss of these molecules, right. So, for any ith layer if I am talking, so something is coming from I plus 1 layer, right, but in I plus 1 layer also something is coming from I plus 2 layer, right. So, it is balanced, right, and in ith layer something is evaporating from ith layer and that is going to I minus 1 layer, right. So, these all terms which are written here. So, first term if I look at here, or f times theta I minus 1. So, I am writing a equilibrium for ith layer, right, on which something is evaporated from ith layer and that has been adsorbed in I minus 1 layer, right. So, earlier we wrote this term something like k I minus 1 times p times theta I minus 1, and the same term has been, instead of writing that k I minus 1 times p, we have written it in terms of f, right, where f is nothing but the flux. So, and so basically your this term is something like your k I minus 1, right. So, that is what the parameter which you are defining is written in terms of the flux, right, and this is your desorption term now, right, because the molecules are desorbing from ith layer. So, you wrote it k minus, right, I theta I, right. So, k minus I means desorption rate constant, and that will be depending on the activation energy for the desorption, because it is a function of temperature, right. So, and nu is the frequency factor just like in your Arrhenius equation. So, nu times e to the power minus E d upon k b t times theta I, right. So, this is the term which is relating to the effect of temperature also on desorption, right. So, this is now the first term which is rate of condensation on I minus 1 layer, this is rate of desorption from ith layer, right. This is f theta I, that is the adsorption on the ith layer, right. So, where from I plus 1 layer, right. So, rate of evaporation from or desorption from the I plus 1 layer, that has come to this layer, right, and whatever the desorption from here has come here into this, right, and this is the meaning of dynamic equilibrium, and at equilibrium there is no net change. So, this term is 0. Right. So, you can you can now simplify this equation, because we have certain assumption now that for first layer the activation energy is different for bare surface, but for subsequent layers the activation energy of each layer is same, right. So, E d activation energy for desorption for subsequent layers, right, when I is greater than 1, then it is same, just like heat of adsorption we have used, right, and K 1 is not equal to K 2, but K 2, K 3, K 4 and they are equal for the multilayer, because it is same kind of molecule which is adsorbing on the same surface, you can see here, because we have already assumed now E d is same, right. So, one can simplify the expressions which I have just written. So, d theta by 0 by dt for the bare surface, right. So, rate of adsorption on the bare surface will be equal to rate of desorption from the first layer. So, that is the equation here, right, and so theta 1 can be correlated. So, basic idea is that we are trying to find out, because theta 1 plus theta 2 plus and so on theta n is to be known, right. So, theta 1 is equal to f by k 1 times theta 0. For first layer, if you write now the same equation, right, because you have already calculated here theta 1, right. So, you can very easily simplify this equation. So, theta 2 comes out to be f by k 1 times theta 1, right, and when you substitute this theta 1. So, this becomes f square times theta 0 divided by k 1 k 2, right, and so on so on. So, you can have for any ith layer this theta I plus 1 is equal to f by k I times theta I, and that can be substituted in terms of theta I. So, it becomes f I plus 1 times theta 0 divided by k 1 times k 2 to the power I. So, this is a generalized form of equation for ith layer, right. So, now what I mean to say, you have determined theta 1, theta 2, theta 3 and so on so on, but still this is to be written in terms of theta 0. So, theta 0 has to be find out, right, because once theta 0 is known, then each term can be calculated and then you can find out sigma of theta I or I theta I, right. So, for theta I we just correlate the total coverage or theta 0 calculation, right. So, total coverage theta t, which we are defining now fraction, right, n a divided by n 0, right. So, total number of molecules adsorbed, and n 0 is the molecule when it is monolayer V m, right. So, that is nothing but sigma of I theta I, first layer, second layer, third layer, so on so on, add all these layers, because these are the molecules which have been adsorbed on the surface. So, you can, this is a kind of mathematical equation now. So, k 2 by k 1 times theta 0 sigma I 1 to infinite I f by k 2 to the power I, right. You must have done these kind of solutions here, sigma I 1 to infinite I x I is equal to x over 1 minus x whole square, right, simple mathematics. You have to just add it to the infinite series and expression. So, that is what the idea here, we have just divided the term or separated the term in terms of k 2 by k 1 theta 0, and rest of the term have been taken in terms of I 1 to infinite I x, which is f by k 2 to the power I. So, just this is your f by k 2 is your x. So, you can very easily write k 2 by k 1 times theta 0 f by k 2, this is your x, right, divided by 1 minus x whole square. So, this is 1 minus f by k 2 whole square, right. So, this is the mathematical expression which can be solved, right. I think this is 1 over 1 minus x. So, I will just check it and this is 1 over 1 minus x solution of this x over 1 minus x, not x square, right. So, that will be f by k 2 1 minus f over k 2, right. So, the same expression here if you look at now sigma of theta I, the first term was I theta I and this is sigma of theta I, that is addition over a monolayer, right. So, here again theta 0 bare surface plus the fractions which are already covered. So, I is equal to 1 to infinite theta I and that can be rewritten as theta 0 plus I is equal to 1 to infinite theta I is nothing but k 2 by k 1 theta 0 f by k 2 to the power I, which is again based on this expression which we have already done before also. So, I is equal to 1 to infinite x I can be rewritten I 0 to infinite x I minus 1, right, because the first when it is 0 it is just 1. So, we can write I 0 to infinite and this I 0 to infinite x I is equal to 1 over 1 minus x, right, 0 to infinite x to the power I is nothing but 1 over 1 minus x, this is summation over a series, right, for infinite series you can check it and minus 1. So, that is already there. So, this gives you x over 1 minus x, right. So, it means our x is this f by k 2. So, this expression becomes theta 0 times 1 plus this whole term k 2 by k 1 and summation over this which is now f by k 2 which is this x over 1 minus f by k 2, right. So, you can very easily simplify the expression, right, which is given over a series up to infinite series and you can simplify it and this is the expression. So, once these two are known, so theta 0 is known now, right, because this is your theta 0 which is summation. So, we can very easily write theta 0 which is equal to 1 plus k 2 by k 1 f by k 2 divided by 1 minus f by k 2 to the power minus 1 minus 1. So, this expression for theta 0 which we need to calculate from here, that has been calculated in terms of theta I, right, because this expression we had already defined here in terms of theta t, right. So, once theta 0 is known, then you can go back to your original expression where theta t was written in terms of theta 0, right. So, this is the expression for theta t. So, that was our original equation 4. So, theta t can be calculated now because theta 0 has been substituted, right. So, k 2 by k 1 times f by k 2 this term divided by 1 minus f by k 2 plus k 2 by k 1 f by k 2 and this whole term in bracket multiplied by 1 minus f by k 2, right. So, this f I told you is related to pressure, right, and C is the term which we have correlated earlier in terms of exponential of heat of adsorption in the first layer minus heat of condensation or liquefaction for the subsequent layer, and that was related to the activation energy for that subsequent adsorption and activation energy for the desorption. So, basically this k 2 by k 1, right, k 2 is the for the second layer, k 1 is for the first layer, right, where the adsorption is taking place which I said first layer and then subsequent layer it is k 2, k 3, k 4 something like that. So, that is the ratio of desorption rate constant for the second layer to the first layer, right. So, that means the C which we are writing exponentially, this you can see from here because C we have this already we have defined it in terms of exponential powers here, right. So, these two terms which we are talking in terms of desorption in the first layer I is equal to 0 when I am saying bare surface, right, and then for the first layer if you are writing 0 and first, right, because for subsequent layers it is same. So, this C is basically for a bare surface and the subsequent layers, right. So, heterogeneous surface and where the homogeneous, where the liquid molecule is already available on the surface and another gas molecule comes and adsorbs, right. So, this is basically related to enthalpy or activation energy for the desorption and the adsorption. So, you can and F we have already defined in terms of the probability of striking, right, that is flux. So, that is related to pressure. So, F by k 2 is basically P by P 0, right. So, we have correlated that F which is already in terms of P divided by n 0 under root 2 pi m k b T, right. So, if I write F by k 2, so that can be correlated in terms of pressure, because in one way I am writing it is K rate constant for adsorption times P, right, times theta, right. So, that K 1 times P is your term which is F, right. So, we can correlate it in terms of the rate constant, and that is for the multilayers, that is homogeneous surface, and the your flux which comes to that surface, number of molecules which comes and strikes to the surface. So, basically F is related to something like a pressure term, right. So, that is what we have defined earlier also. So, this is your F value. So, F by K 2 I have written here, right. So, F divided by K 2, and that whole term we have called now x, right, a constant, just to simplify the expression. So, now if you just write it in form of P by P 0, which is F by K 2, that I have already discussed, that is your x. So, your equation which we are talking x is the ratio of adsorption and desorption rate from the second layer and higher. So, how many molecules adsorbs and how many molecules desorbs, right, for subsequent layers. So, you can find out and correlate it, because P 0 is the saturation pressure and P is the pressure, right. So, at saturation no further adsorption takes place. So, when P by P 0 reaches to 1, right, then your total coverage theta t approach to infinite, that I have said that the layers are completed, right, or this is nothing but at this is the point where condensation starts, and the capillary condensation phenomena which we are discussing for nitrogen adsorption desorption isotherm. So, pores are totally filled, right. When pores are filled, nothing can be adsorbed now, right. So, it means the BET isotherm validity is up to a certain ratio P by P 0, because after that the capillary condensation phenomena starts, right, and then isotherm is no more valid, correct. So, this is what the adsorbate condensates into the multilayer on the surface. So, capillary condensation phenomena starts in micropore. So, at saturation pressure of gas, an infinite number of adsorbate layers built up on the surface. So, now how to use this isotherm, because now we have discussed this isotherm, the derivation of this isotherm and the meaning of C, which is related to the adsorption and desorption activation energy or heat of adsorption on the bare surface and heat of condensation on the subsequent surface. So, these parameters can be determined experimentally also and by using the isotherm equation. So, when you do that, so when we, because now our interest is to find out the surface area of the solid catalyst. So, to proceed, for any unknown sample, right, the a given mass we have to put, right, in a small volume and cooled to a lower temperature, something like 75 Kelvin, right, for nitrogen. So, generally 77 Kelvin or 75 Kelvin is the condensation temperature of nitrogen. So, what you have to do in the specified chamber, right, like what you call BET apparatus. So, you put a given mass of catalyst and over that you allow the nitrogen gas in presence of some maybe a helium also or nitrogen itself, that is passed through the sample, right, under you have to calibrate the system first. So, helium can be used for that, and then you place a Dewar flask which contains liquid nitrogen, and that will allow the gas to adsorb, right, and then you measure through a detector the volume of the gas which is adsorbed as a function of pressure. You need not to go to P 0 value. So, you can define the points. So, P by P 0 value, and then you can find out the number of molecule adsorbed, and then you can use this isotherm, right, because this is nothing but a linear form of isotherm, where we are just plotting P upon V into P 0 minus P versus P by P 0. So, this will be a straight line, right. So, the meaning is that if I have this isotherm, so we have a linear form of this equation now, which I can write here again. So, P upon V into P 0 minus P, the same isotherm what we have derived here is in the linearized form. So, I am just writing it again here. This form of isotherm, right, this is your BET isotherm, where when we write it in terms of fraction. So, a plot of this P upon V into P 0 minus P is equal to 1 upon V m C plus C minus 1 upon V m C into P by P 0. So, a plot of this, that is P upon V into P 0 minus P versus P by P 0 will be a straight line like this, right. So, this can be the linear form or non-linear form can also be used by using the softwares, right, regression technique. You can use the non-linear regression technique or linear regression method, and you can find out the parameter, because this is your interception of this, right. This is your interception I, and this is your slope S, C minus V upon C m, because this is times the P by P 0 here, right. So, this C minus 1 upon V m C is your slope, right. So, from these two you can find out the surface area or V m value, because first we have to find out V m, right. So, this can be used to determine the surface area. So, same thing has been discussed here, that you allow the gas to adsorb and then measure the volume of the gas adsorbed as a function of partial pressure or pressure of the gas. So, at when there is an equilibrium, that is P 0, right, which will at temperature 75 Kelvin, the pressure is roughly 750 millibar, right, that is the saturation pressure of nitrogen. So, amount of gas adsorbed either in terms of number of molecule or volume is then measured as a function of pressure and can conveniently be expressed in terms of amount of gas adsorbed in one monolayer. So, we are interested in having a monolayer V m or N m, which is given here now, right. So, this is the number of molecules of the gas, total number of molecule of gas which adsorb on the surface, right, and this is when the monolayer forms, right. So, this is something related to V m which I have written here, and this is the volume which is adsorbed for the total number of layers which are I theta I sigma, right, in that layers. So, basically you know P v is equal to N R T. So, we are applying that law here. So, number of molecule P v is equal to N R T. So, N has been calculated, right. Same thing for N has been calculated at monolayer, right. So, this gives you V upon V m, which I just said before, right. So, by substituting this in your equation which we have derived earlier for theta t and just rearrange that. So, you have the expression like this, P upon V into P 0 minus P. So, basically this is your V, not V m, is equal to 1 upon V m C plus C minus 1 upon C V m P by P 0, which I just said, right. And so, this is your interception. So, I called it I, and this is your slope. So, I called it S. So, this can be used to determine the surface area of a solid. So, plotting P over V into P 0 minus P versus P by P 0 will give you a straight line with a slope of S, which is C minus 1 upon C V m, and interception I 1 upon V m C. So, you can very easily solve these two equations and you can find out V m is equal to 1 upon slope plus interception I plus S, right. And once that is known, the volume of V m, that is this, can be converted into number of molecules adsorbed, right, by N 0, which is equal to P into V m upon R T, as I said before also. And if the area of one molecule is known, then your B T surface area is nothing but N 0 times alpha, right, area of one molecule multiplied by the number of molecule in the monolayer. So, this was the data, how to use the data, because as I said, if you had used the Langmuir adsorption isotherm, it will show a monolayer here, because it does not talk about multilayer adsorption. So, Langmuir isotherm will talk a V m value here, right, but B T actually the V m is here. So, your Langmuir adsorption isotherm, if you calculate the surface area from that, it will always be higher than your B T surface area, because B T isotherm has removed those multi molecule or multi layers, right, compared to the Langmuir. But when it is a chemical adsorption, then both these areas will be equal, because that time though no further chemisorption is possible, right. So, basically when you take the data or when you generate the data for this determination of surface area of a catalyst or then same thing can be extended for pore size distribution also by nitrogen adsorption desorption method, which is your capillary condensation. So, you have to just consider the normal boiling temperature, that in nitrogen generally adsorbs at this, as I said 77 Kelvin, right, minus 196 degree centigrade or 77 Kelvin is measured over a wide range of partial pressure, which is below 1 atmosphere of saturation, 750 what I said before also millimeter of mercury. So, identify the amount required to cover the entire surface by the monolayer, right. So, this is a monolayer. So, generally P by P 0 less than 0.1 is a monolayer, and when P by P 0 reached from 0.1 to 0.4, a multilayer starts, and beyond 0.4 it becomes a capillary condensation. So, we need not to, when we have to determine the surface area, we need not to go to this range, right. When you have to determine the capillary condensation of pore size distribution, then you have to desorb it also, right. Desorption isotherm has to be used, then you have to fill the pore or saturate the pore first, right. So, this generally up to 0.3 you can generate the data for this isotherm, right, to check, or just 0.1 is also sufficient. So, how many data points are required, that you have to check on a priori, and one can use this isotherm very easily for determination of surface area. So, Langmuir isotherm, as I said, it is something like that, theta is equal to Kp upon 1 plus Kp. So, if you just linearize this, theta is your V by Vm, right, volume of gas adsorbed divided by monolayer coverage. So, P upon V is equal to 1 upon K Vm plus P upon Vm. So, a plot of this P upon V versus P is a straight line, and you can find out monolayer, right. But for physical adsorption, this value will be higher, so not very right. BET isotherm we have already discussed now. So, P upon V into P 0 minus P is equal to 1 upon V m C plus C minus 1 upon C V m times P by P 0, where P 0 is the vapor pressure or saturation pressure, right. So, P upon V upon divided by P upon V divided by P 0 minus P versus P by P 0, it gives you a straight line. Find out this slope and find out interception and solve it, right. Then once that V m is known, because from this graph you get the V m. So, then you can calculate, because alpha is the area covered by one molecule, as I said before. So, surface area is V m times N 0 divided by 22,400, which is your V reference basically, right, into alpha, area covered by one molecule. So, alpha I discussed yesterday is the projected area pi r square, right, where r is the radius of the molecule. So, nitrogen, right, which is adsorbing on the surface. So, that is F times I told a packing factor. So, basically that is 1.09. So, it becomes 1.09 times m by n 0 rho to the power 2 by 3, where m is the molecular weight of the gas, n 0 is the Avogadro number, and rho is the density of the liquid nitrogen or density of the gas at adsorption condition, right. So, remember this is the density of the liquid nitrogen, because the condensation is for liquid nitrogen, right, or density of the nitrogen at 77 Kelvin. So, this value is written here 0.808 gram per centimeter cube, roughly at that condensation temperature of nitrogen gas molecule, and alpha it gives you roughly 16.2 angstrom square, which can be used, right. So, you can very easily find out the surface area, that will be for given mass. So, divide by mass of the catalyst. So, we call that specific surface area, right. So, these are some of the data. If you look at from literature, a lot of literature is available for different kind of solid material, right, and you can use them. So, silica gel roughly has the average pore diameter of 10 nanometer and surface area roughly 200 meter square per gram. At different, if you have different treated silica gel, it can have surface area 6, mean diameter 6 nanometer and surface area 400. So, different kind of areas may be available from the same solid material, depending upon the catalyst preparation, sintering, aging temperature, right, you can have the variety. Same thing for gamma alumina, say surface area roughly 150 and it can be 500 also. So, pore size 10 nanometer average, right, and 5 nanometer smaller the pores, right. So, pore size is related to surface area. If you just look at the a cylindrical geometrical pore, straight cylindrical, if I say if radius is r, right, and pore volume is V g, right. So, V g generally I said pore volume, right. So, V g unit is generally defined centimeter cube per gram of the catalyst. So, so what is V g? V g, if I talk a cylinder of this pore length, average pore length L bar, average radius R bar. So, total pore volume, right. So, average pore radius I am talking. So, that is simply pi r square into L, right, something like this average, and I will say here R bar and times the whatever, because this is the pore volume. So, times the number of pore, right. This is for one pore. So, average pore radius has been defined, average pore length has been defined, and if there are n number of pores, you can write it like this. What is S g? S g is the surface area of that catalyst. So, surface area is not the external, right. It's not, suppose if I say a solid pellet and this is not that radius or surface area of that solid, it is the area because of these pores, right, cylindrical pores, right. So, if we have already defined, so surface area is basically for a cylinder 2 pi r bar L, right. So, that will become 2 pi r bar L for one pore, and the n number of pores. So, it is like this. So, I can very easily develop a relationship between these two, that if you just divide these two expressions. So, you will have average pore radius r bar is equal to 2 times V g divided by S g. So, this can be used to determine the average pore size, right. So, smaller the capillary, so there may be larger number of pores in the same solid, right. So, microporous material, mesoporous material, so like that, right. So, this is generally used to determine the average pore size of a catalyst for a given mass. So, same thing for zeolite, you know zeolites have the smaller pores. So, 0.6 nanometer can be the average pore size or diameter, right, and the area can be between 400 and 800, right, meter square per gram. So, same thing activated carbon, you can see it can have the area up to 1200 meter square per gram. So, different metals, different catalysts can be used for methanol synthesis, copper zinc oxide on alumina catalysts have been tested, ammonia synthesis, iron, alumina and potassium oxide as a promoter have been tested, right. Reforming platinum, rhenium, alumina has been used, right, or is being used also. Same thing for epoxidation, right, in petrochemical industry, the ethylene oxidation, right, resins formation. So, silver based catalysts are used on alpha alumina. So, different catalysts can be used, have been tested for different process, and the surface area and the pore size or pore size distribution strongly depends on the pore geometry, catalyst preparation, right, raw materials, aging, drying, which is very crucial. So, we have already discussed these things last time also, but since the condensation phenomena takes place and based on that we determine the pore size distribution, that is capillary condensation when you have nitrogen adsorption desorption method. So, basically it is a BET method again, right. The only thing that you are going towards saturation or you are applying higher pressure and then calculating, right. So, your T plot method which generally used to find out the thickness, right, and same thing the adsorption desorption which is used for pore size distribution and volume of the pore, and same thing for the mercury penetration method. The approach is based on surface tension effect, but the same fundamental thing, pressure is applied and then we calculate delta V, right. So, in the case of nitrogen when we talk, we have this term adsorbed layer thickness. So, we have to find out, right, this also. So, a T plot is to be done where this can be plotted as a function of size of the pore, right, pore size, right, and you can find out the surface area also from the slope, right. So, this is to be compared with a non porous material, right, then only you can do that, because in non porous material there will not be any pore. So, only this thickness of the adsorbed layer will come, right. So, that is why yesterday we were talking 0.305 nanometer. So, that is that for nitrogen, where that is one monolayer form, that Tm will be that, right. So, how many layers have formed, you can you can calculate and correlate it with that adsorbed layer thickness, and that will be required when you find out the pore size distribution, right, because your capillary condensation will give you, or Calvin equation gives the radius which is beyond that T value, right. So, this is what you get from the Calvin equation or condensation method, right. this is already adjob layer, this is an adjob layer, right. So, this plus T. So, T has to be determined. So, as I said, Wheeler's model can be used for finding out, and this thickness may be a function of pressure, right. Adjob layer thickness relates to the pressure. And hysteresis, again you can get the idea about the type of pore, their complex nature, because the adsorption, desorption hysteresis which you get because of these kind of ink bottle effect here, there may be kind of wedging, right. It is a slit type pore. So, you will have a different kind of adsorption, desorption hysteresis in these kind of pores, right. If pores are straight cylindrical, you will not get any hysteresis, right. So, this we have discussed last time, and this is the Calvin equation which relates the vapor pressure, right, required to condense the nitrogen gas in a capillary, right. So, pressure is related with the radius of that capillary here, right. So, R sigma we have talked surface tension of the nitrogen, V is the volume, right, or the molecules of the gas liquid nitrogen, right, and theta is the contact angle which was taken 0 because it is a wets the surface, nitrogen wets the surface, right. So, T method which is BT only valid for small pressure intervals. So, only you have to look at the pressure differentials, very narrow range pressure differentials P, and then go P plus delta P in a smaller range 0.01, right, variation whatever the in pressure, right. So, that is very important. So, thickness of the adsorb layer can be calculated, and this is for the one layer what I was talking for nitrogen roughly 0.354 nanometer, right, Tm, right, but you have to calculate the multi-layer thickness. So, that can be determined. So, plot of thickness versus pressure for a non-porous material is the same, right, and that has have been so many R&D has been done in this and checked experimentally. Then when you plot the thickness versus pressure for a non-porous material, nothing will condense in the capillary, there are no capillary, right. So, only it will be thickness of the layer adsorb layer or Tm monolayer. So, that can be used to calculate the Tm value, right, this for the non-porous material. So, two plot can give you the idea how to interpret or check the complex nature of the pore by looking at these data, right. So, the pore volume pore size distribution PSD. So, that is again important when you look at, because one thing is that you can determine the average pore size, right, but that is not a correct way of representing the pore size when you have a bidispersed pore or different type of pores, right. So, one pore or some pores may have a diameter of say 50 nanometer and other pores have a diameter of say 500 nanometer, you cannot compare these, right, your results may entirely different. So, you have to just look at the distribution, that what fraction of the pore or what fraction of the pores have this much volume and what is the pore size distribution, right. Same thing for the second, if there is a wide variation in the pore size. So, Calvin equation is this. So, now I have written here R k because this will give you the Calvin radius, right. So, and this is to be added in the find out the total pores, right. So, that is some empirical correlation which is to be used to find out T. So, I can write it T here R k plus T, right, thickness of that layer adsorb layer, right. So, that is your radius of the pore, right, where this thickness can be determined by this. So, thickness is a function of pressure as you have seen here, right. So, this roughly comes 4.3, this is the same equation. So, 4.3 times 5 divided by ln of P 0 by P to the power 1 by 3, because last time I told n is 3, right. So, Wheeler, this is basically Wheeler's model. So, we can find out the thickness of the adsorb layer, and now if you nowadays the softwares are available, right. If you just have the instrument, then these are already available in the softwares, and where you have to just generate the data in terms of pressure as a function of volume adsorbed, and then the software calculates all these things and it gives you the data. But we have to see here that how these data have been generated, right. So, just I am looking certain steps, or briefly I will or quickly I will just go to these steps, right, which are generally used to give a complete characterization of the catalyst, which is something like for different kind of solids, right, a plot something like this, right. So, the data which is generally used, right, raw data will be something like P by P 0 versus pressure, and then we have to calculate this Calvin radius, right, and then thickness of the adsorb layer, which is also a function of pressure, right. So, you can see that this thickness of that job layer may vary from 16.4 to 7, right, in angstrom unit. So, there when the pressure varies, then thickness may also vary, and then you calculate the difference in volume, right, that delta V for an incremental pressure P, what is the additional volume which have been adsorbed when you change the pressure from P to P plus delta P, right, and then you calculate the ore radius R k plus T, right. Then you calculate what is the additional thickness of the layer which have been increased, which has been increased rather between two successive pressure changes, right, and then you calculate. So many things are required here. If you look at when you look a complete characterization, so which can be a T plot, which can be a Barrett, Joyner and Hollanda plot, right. There are different kind of softwares or packages or theories available to determine these, right. So, the salient points which I am talking here to find out this. So, I have just written certain steps. So, first thing is that calculate the Kelvin equation, right, R k. So, compute Kelvin radius in the unit of angstrom, and that equation we have already talked, this one, right, Kelvin radius. So, which for nitrogen as an adsorbate, surface tension of nitrogen is 8.85 into 10 to the 5 minus 5 Newton per centimeter, right. Molar volume of nitrogen we talked yesterday also, roughly 35 centimeter cube per gram mole, right. So, R k is roughly 9.53 divided by ln of P 0 by P. So, this is the same equation 9 which have been now simplified after substituting the parameters. Sigma has been substituted, R is the gas constant, T is the temperature in Kelvin. So, one can very easily find out this R k, Kelvin radius, right. So, at different pressure of the gas you have different Kelvin radius, right. So, this is given in table 3 as I shown, and we will just look at that. So, Kelvin, once you have the data in terms of P by P 0 versus P. So, your data is something like at different pressure you are generating P by P 0 data and then recording in terms of volume of the gas adsorbed, right, at a given condition of temperature, right. So, so you are generating these data, and then once this is, because your P 0 is known now, right, saturation pressure is known, P is known. So, you can very easily find out what will be the Kelvin radius at that condition, right. So, the first one, then once this is known, then find out the adsorbed layer thickness T again from this equation, because both terms are known, P is known, P 0 is known, saturation pressure. So, thickness can be calculated, right. And once thickness is known, you can find out, because you have already measured the volume, right, at given pressure P and P plus delta P, what is the additional increase in volume. So, delta V can be calculated, right. So, volume adsorbed is calculated by difference between the successive values in column 2. So, I will just discuss this next time. So, I stop here and we will continue it next time.